So here we are with the conundrums we have to explain. Essentially, if you assume tropical motions are of the order of 10 to the 6 meters, then you get the strong barotropic structure, and then it's a problem to explain how convection could be driven. And Charney put this in terms of tropical convection being driven by extratropical forcing. Okay, to read his own words from the book, the picture of the tropical circulation that emerges is quite different from that of conventional Hadley circulation. The rising motion is much more concentrated in a narrow band and does not necessarily occur at the equator. So he's talking about the ITCZ, which we have seen already and we will see again, is actually shifted to the north with the South Pacific convergence zone and the South Atlantic convergence zone and the Indian Ocean that kind of splits during the summer because of the monsoon and the warm ocean. So the subsiding velocities are small and spread over a large area, the subtropical highs, and the circulation is not necessarily symmetric. We already know that the ITCZ is not symmetric. The quasi-non-divergent source-free flow, quasi-non-divergent, so barotropic source-free flow acts to transfer lateral influence from the extratropical circulations to the intertropical convergence zone, so that the position of this zone is determined by the extratropical circulation in both hemispheres. So this is a very different interpretation than the understanding we have since, but we have to give Charney a break because he didn't have many of the observations that came about after he had already done these arguments. Of course, the problem with this was that the extratropical forcing doesn't provide enough energy to create these kind of tropical motions. The waves are too large scale, too weak by the time they reach the tropics and so on. So essentially this was not very well explained using the order of 10 to the 6 meter scale and the associated vertical structures and observations of convection. The hypothesis 2 then says that convection occurs because of reduced static stability in regions of convection. As we said, this is a bit of a circular argument because doesn't explain where the convection itself would come from, but convection obviously mixes up and reduces the static stability. Going to our energy equation, we've seen this already 100 times, where the heating in the atmosphere explains the variability of the potential temperature, and we did the scaling arguments and looked at the vertical scale and its relation to the horizontal scale with the Richardson number, which is about converting the potential energy to kinetic energy when the Rossby number is of order 1, right? So the relation between the vertical motion and static stability related to the condensational heating, or relating to the static stability to the Brunt-Väisälä frequency. Remember, this relates to d theta dz 1 over theta as well. Then is approximately explained dimensionally by the heating rates and the enthalpy or thermodynamics, right? So in that case, as we already said, the vorticity equation can give us at the macro scale or 10 to the 7 meter scale a different balance where the acceleration term is balanced by the stretching and divergence terms. So you can relate the lower part of the atmosphere to the upper part of the atmosphere with Rossby numbers less than 1. Of course, here, even if f goes to 0, you have relative vorticity, right? We said zeta is the relative vorticity and this is the planetary vorticity, and we have zeta plus f, which is the total vorticity. So when you move the vortex tubes and stretch them and compress them by divergent flows and advection, you can create these baroclinic links. Looking at it here, you have a rapid ascent, so heating rates are shown here. The latent heating is going to give you positive source, whereas you have a rapid descent which has got negative, and you have this broad slow subsidence where adiabatic compression and heating is going to be balanced by radiative cooling over the subtropical highs. And going from the convective heating to this region, you're going to have broad inversions because of that balance of adiabatic compression and radiative heating. To read the caption, the schematic cross-section of the tropics illustrating the relative areas of ascending and descending air. Rapidly ascending air occurs in conjunction with convection associated with the release of latent heat that we are seeing here. That's the latent heat of condensation. Beyond convective region, there are large areas of descending air as a result of radiational cooling to space. The condensational heating and radiational cooling is almost balanced by adiabatic cooling and heating respectively. Okay, so you have rising air expanding and releasing, condensing the water vapor, releasing heat, and then as it rises there is radiative cooling happening as well. So this can give you kind of a local vertical balance that can be placed within this broad weak temperature gradient that we were talking about, so that the advection terms can still be small, but you can have strong vertical balances. So the condensational heating and radiational cooling is almost balanced by adiabatic cooling and heating respectively, with given equation 3.3 which we will look at. This forms the basis of weak temperature gradient approximation that's discussed in the text. So the lower panel provides a very simplified view of columnar heating and cooling in different regions of a tropical disturbance. So you can have rapid ascent and descent. When there is deep convection and rapid ascent, there is immediate descent or pulling down of the air and entrainment of momentum and colder air and so on and so forth, which go into the details of the structures of convection that we are not going to look at. But you can see that it can give you heating rates of over 5 Kelvin per day, which is massive, whereas the heating rates here are basically cooling of the order of 1 Kelvin per day, and it's over a broad region, and there is a balance between adiabatic compression and radiative cooling, as we said. This paper looks at the weak temperature gradient balance at the MJO scales, looking at changes in moisture, dynamic response in terms of the surface fluxes, enthalpy fluxes associated with the moisture convergence, and the entrainment and precipitation processes associated with changes in convection, and a gravity wave adjustment that produces dynamical response when convection happens. So this gives you a sense of how low-level moisture convergence, without saying whether it's happening within the boundary layer or above the boundary layer, relates to upper-level adjustments producing dynamical response. Lot of arguments, but basically we have to explain the context of generating dynamical responses in the deep tropics within the background of weak temperature gradients and near barotropic structures, and the large-scale hydrostatic balance, which we argued is still valid. So that's where all the nonlinearities of the moisture dynamics come in, and the spatial scale of 10 to the 7 then becomes very critical to create this non-divergent baroclinic processes or divergent baroclinic processes, which can generate and store potential energy and convert to kinetic energy of dynamical responses. I hope it's clear. It's I'm using a lot of words, but unless you understand the details of the mathematics, we do have to go with the words.